So good evening and good afternoon, good morning to Josh for getting up very early and coming online for participating in the seminar. We are very happy to have him. He will be speaking on symmetries in the sequences of Betti numbers and Bass numbers for us today on complete intersection rings. So Josh, it is over to you.
All right, yeah, thank you guys for the invitation to speak. Yeah, so I want to talk about joint work with Ben Briggs, who's at MSRI, and then Daniel McCormick, who's a graduate student at the University of Utah. And yeah, the theme of today is talking about the asymptotic properties of Bass and Betti numbers over a complete intersection, but also, I mean, a lot of the things I'm going to say work a little more generally, but I'll try to tell you about that as we get there. So let's go and get started. So throughout RMK will be a commutative Noetherian ring, local. And we'll go ahead and fix a finitely generated R module. And I mean, a lot of the things I'm going to say, I mean, kind of the right context is actually thinking about a complex of R modules with finitely generated homology, but I can stick with this at least for the beginning of the talk. And the theme is we're interested in asymptotic properties of Bass and Betti numbers. Okay, and so just to set the notation for the rest of the talk. So just to remind you, the ith Bass number, sorry. Well, what is it? It's just the K vector space dimension of X, R, I, K, M. And I'll go ahead and denote this with mu I of M. All right, and so what this is, and I'll write this down in a second, but this is supposed to be some notion of the size of a minimal injective resolution of M. And then the ith Betti number is, so kind of dual to the definition above, right? So it's the K vector space dimension of this X module. Well, now I'm looking at MK versus KM. And so just as a remark, these are supposed to be measuring kind of sizes of minimal injective or minimal free resolutions of M. So what the ith Bass number measures is it measures the number of copies or the number of direct summons of the injective hole of the residue field. The ith piece of a minimal injective resolution. Whereas, I mean, I think we're a little more familiar, or depending on your perspective, you know, the Betti numbers are measuring just the ranks of the free modules. So the rank of the ith free module in a minimal free resolution of M. Okay, and so what we're interested in is putting these numbers together and forming, you know, the Bass sequence of M and then the Betti sequence of M. So the sequence of Bass numbers and the sequence of Betti numbers, and we're interested in the asymptotic properties of these two sequences over different rings. And so going back to the theorem of Oslander, Buxbaum, and Serre, the following conditions are equivalent. So the first one is that R is a regular ring, so a regular local ring. The second is that, I mean, I guess typically I'd say that the Betti numbers eventually vanish. Third is that the Bass numbers eventually vanish. All right, so I guess the motto here is that over a regular local ring, these Bass and Betti sequences for modules eventually all vanish, right? And if they're modules, of course, they vanish in some finite range. But for complexes, you know, you're just getting eventual vanishing. And so what I'm going to be talking about today is kind of, we're just going to weaken the singularity slightly and talk about complete intersection rings. And we want to study these Bass and Betti sequences for those rings. And I mean, there's already kind of a rich history, so this isn't, I'll try to mention this as we get there. But so that's what we're going to do. So now we're going to, for the rest of the talk, we're going to look at when R is a complete intersection. So. Okay, so what I mean by that is, of course, is that just, you know, when you write the completion as a regular local ring modulo some ideal, and let's say the F's are in the square of the maximum ideal. So this is a minimal Cohen presentation. What we require is that the F's form a Q regular sequence, right? So a regular sequence. Okay, and so, of course, the basic example of one is just going and looking at a power series ring modulo powers of the variables. Okay, and so what we're talking about today is Betti and Bass sequences over such rings. And let's start with an example. So let's start with the case that C is 1. So in this case, R is, you know, just a hypersurface ring. Okay, and so Eisenberg's theory of matrix factorizations actually tells us asymptotically what happens to every minimal free resolution. So Eisenberg, 1980, I guess, described the tails of minimal free resolutions. Over R. Namely, when I look at, let's say, the minimal free resolution over R of my module M, when you start to resolve it, you get to some point where eventually you get constant ranks. Right? Oops, sorry. So maybe, sorry, let me. So from here on, or wherever it starts, eventually the resolution is 2 periodic. Eventually. Two periodic, so when you go ahead and try to write the differentials as matrices, it just repeats as A, B from then on, and the ranks of these free modules that are appearing are constant. So in other words, what this is saying is that the Betti numbers of the module are eventually equal to this number, this constant rank, this stable rank for M. So there's just some non-negative integer for which the Betti numbers eventually are always equal to that. Okay, and so I don't think this is this isn't anything new, but you could just ask, okay, that's what happens for the Betti sequence. So what happens for the Bass sequence? Sorry. It's a natural question. So this is again over a hypersurface ring. Okay, and so let's just analyze this case. So just to remind you, so when I'm looking at this Bass number, I'm looking at the K vector space dimension of X, R, I, K, M. And so let's just examine this X module. Okay, so R being a hypersurface, just being a complete intersection, means that it's Gorenstein. So when I look at kind of the Gorenstein duality functor, or just R Hom like R, M itself is reflexive. So M is isomorphic to its double dual. And if you don't want to think about it this way, one way to think about it is over over a Gorenstein ring, right? This Betti sequence, or sorry, this Bass sequence is going to be invariant under taking syzygies. So you might as well pass to M being a high enough syzygy. Sorry, taking M, you can pass to a high enough syzygy, and then you have an MCM module, and then you can just imagine that this is an ordinary dual if you'd rather think of it that way. But regardless, okay. So just using that R's Gorenstein, you have this. And then just messing around with Hom tensor adjunction, which you can get this derived Hom tensor. You have this right here, and when I stare at this, this is just R Hom R K R. And again, R being Gorenstein tells me that when I compute the homology of this, this is concentrated in a single degree, just namely the cohomological degree is D, where D is the dimension of R. And so what you end up finding out is that this is the same thing as X, R, I. I'm not too worried about whether it's a plus or minus because we're only interested in asymptotic properties. And this is where D is the dimension of R. Okay, so what's the upshot of this calculation? The upshot is that if I'm interested in the ith Bass number of M, what I'm really staring at is some shifted copy of the Betti number of the dual of M. And again, if you don't want to think of the derived dual, again, just take M to be an MCM module, and then this isn't the honest R linear dual of M. Okay, but as Eisenberg's theory already tells us, theory of matrix factorizations, this number stabilizes, or sorry, these numbers eventually stabilize to some stable rank, the stable rank of the dual. And then again, it's really another direct calculation that the dual of a module or MCM module has the same constant Betti numbers as the original module itself. So this stabilizes to the rank. So in other words, okay, so let's put this all together. What this tells us is that the Betti numbers, sorry, the Bass numbers of M are eventually Rm, which are also the Betti numbers. So over a hypersurface ring, we don't expect, you certainly don't get, the vanishing that we had for the regular rings, but now we have that the Betti and Bass sequences eventually agree. Okay, so that's the story for hypersurfaces. So let's just up the codimension by 1. So maybe we'll look at this ring, and let's take our module to be R mod maximal ideal squared. And so what you can show is that the Betti numbers and Bass numbers have very explicit formulas. So the Betti numbers, are eventually given. So it depends on the parity. So whether I is odd or even determines what the ith Betti number is. So when I is even, it's given by this polynomial. And when I is odd, we have this other linear polynomial. And the Bass numbers, this one are given by plus 2. I is even. And 3/2 I plus 3/2 I when I is odd.
Josh, there is a question in chat box. It says, is the equality true for complete intersection rings or also arbitrary within local rings?
Oh, no. So yeah, I'm just sticking to, so yeah, definitely not true. I'm thinking, or I'm guessing they're asking about this equality. And
Yes.
Yeah. So yeah, in general, no. But over a hypersurface ring, this is the story. So when the codimension of the complete intersection is 1, then you always have eventual agreement of those numbers. But already here, I mean, over non-Gorenstein rings, like you'll immediately have the Bass numbers of R, right, are gonna go on, but the Betti numbers are 0. I mean, there's plenty of examples, but even here you'll see, I mean, the Betti numbers and Bass numbers don't need to agree. So yeah. But that is kind of the theme of the talk, is that over complete intersections.
So even if codimension is bigger than 2, it is not true.
Yeah. So right, exactly right here. So we would, even in this example right here, if you look at the even Bass numbers, they're always 1 bigger than the even Betti numbers in this example. So you can't expect quality in general. Does that answer your question?
Okay. Yeah. Thank you.
But yeah, but I think you're onto the right idea, is that there is going to be a very strong relationship though. So that's what we're building towards. Yeah.
Thank you.
Yeah. Oh, that's a good question. So yeah, exactly. So that is kind of one of the points, is that over a general complete intersection, there's just no, you don't get honest equality, right? I mean, so this one works out where the odd parts agree, but the even parts don't. Okay. But I mean, you could stare at these sequences, and then you could notice something pretty, you might notice something immediately, is that when you look at the leading terms of these polynomials, all of them coincide. And so, all right, so let me state a theorem. And so really this is a theorem of Lucho-Avramov, but it's building on work of Gullikson and Eisenberg, but I'll state it in kind of its most refined form at the time. So this is the 89 paper. So let's say R is a complete intersection. And again, we'll have codimension C. And M is a finitely generated R module. Well, let's say with infinite projective dimension. Okay, so why do I want to pay attention to infinite projective dimension? Well, the point is that if we have finite projective dimension, we know the Betti numbers are eventually 0. But then over this perfectly good Gorenstein ring, the Bass numbers are eventually 0. So we already know the asymptotics for modules of finite projective dimension, right? We know the Betti and Bass numbers will agree. So let's focus on the infinite projective dimension case. So then for all I sufficiently large, again, this is building on kind of work that was already out there, but I'll just go and say like this. What Lucio showed is that the Betti numbers are eventually given by a quasi-polynomial of period 2, but this quasi-polynomial has a constant leading term. So just like this example up above here, we have a quasi-polynomial of period 2, but the leading term is the same for the 2 quasi-polynomials. So in other words, what he showed is that you can write it as, so this is I to the D, so this is 2D times d factorial plus some lower order term, some lower order quasi-polynomial. Okay, so I'll write that in a second, but also the same story is true for Bass numbers. Okay, so just to quickly, so these two are lower order quasi-polynomials, so period 2. I'm not too worried about the period, so, but I mean, if you're curious, they have period 2. And the point is that, so this is where this this term up here, this term, it's called the Betti degree of M. The Betti degree is some positive integer, and this term right here is called the Bass degree of M. This is also a positive integer. This is where the Betti degree and Bass degree are positive integers. So you can normalize, I mean, this is kind of the usual thing, right? So you normalize the leading coefficient. And the degrees of those polynomials are no more than c minus 1, where c is the codimension. So. Okay, so I know it's kind of a lot to parse, but I mean, let's just maybe go back up to this example above, right? So just quickly, so you have this codimension 2 complete intersection, so C is 2. And what Lucio's theorem says is that eventually the Betti numbers have to be given by, kind of two polynomials that have the same leading terms, where the degree of this polynomial is no more than the codimension minus 1. And in this case, we have a linear polynomial, so that's fine. And then the same story is true for Bass numbers. Okay, and I'll do another example in a second. But I just want to set some last piece of notation. So yeah, so this beta deg, this is the Betti degree of M, mu deg, this is the Bass degree of M. And then this is probably not standard at all, but I'll go ahead and give names to D and E. So some of you may know the story already there. I'll call D the beta complexity, but actually I'll add one to that. And the Bass complexity will be E plus 1. Okay, so this is just notation. Sorry, did someone have a question? I didn't see it.
Yeah, the degrees of beta IM and mu IM, they are different, right?
A priori, yeah. I mean, like at first glance, there's no reason to expect them to be the same. But that's, yeah, exactly. That's, I mean, when we look at this example, yeah, D is 1, E is 1. But yeah, yeah. So the answer is they turn out to be the same, and that was already known. Yeah, and I'll get to that. But yes. Yeah.
Okay.
Yep. Good. So yeah, at first glance, you might give them different names, but they end up being the same thing. So I think nowadays you certainly just call it the complexity of them. Cool. All right. So yeah, let's get familiar with these invariants a little bit. So that example up above. What we saw is that the beta complexity, right? We said D was 1, so the complexity was 2. And the Bass complexity was also 2. So this is what someone was already pointing out. And in fact, in this example, the Betti degree, if we go back up here, when I go to calculate the Betti degree, you have to take this normalized leading coefficient. And so if you just plug in the values, so D is 1, you find out that the Betti degree is 3, and so is the Bass degree for this example. Okay, so Okay, there's a nice and easy example. Let's do another one. So let's do code dimension 3.1. It's a little more interesting. And let's say, again, the module is r mod m squared. So I'm only picking r mod m squared because this one has kind of interesting quasi-polynomial behavior. What you'll find out is that the Betti numbers are eventually given by, again, two polynomials. First one is 9/8 I squared plus 11/4 I plus 1. I is even. 9/8 I squared plus 3i plus 15/8, 1i is odd. And the Bass numbers are 9/8 I squared plus 15/4 I plus 3. And I mean, it's not terribly important exactly the formulas, but I just want to get them down. Odd. Okay. Okay, so let's examine this situation. So just to give the values of the invariants. So the Betti complexity, again, is the degree of these polynomials, but plus 1. So again, the Betti complexity is 3. And then it's the same story for the Bass complexity. And now the Betti degree, once you plug it in with the normalizing leading coefficient, you got 9. And then the Bass degree is 9 as well. Okay, and so you might be anticipating the theorem already. So the theorem, and I'll kind of discuss what was known already. Also, so the theorem with Ben Briggs and Daniel McCormick. So the following is that in this situation, so let's say with infinite projective dimension, then what's always true is that the Betti complexity is the Bass complexity, and the Betti degree is the Bass degree. So in other words, when you go back up to Avramov's theorem, the 89 theorem, it says that when you stare at those two quasi-polynomials that are governing the Betti numbers and the Bass numbers asymptotically, that those two leading terms of those two different polynomials, they have to coincide. So that's the theorem. And the obligatory remark is the first equality has been known for quite some time. I'm only listing it here. I mean, I guess so. Ben and Daniel and I, we work in a little bit more general setting, and we have to prove things a little bit differently. So we kind of have to reprove the Betti and Bass complexity statement. But yeah, so the Betti complexity being the same as the Bass complexity, that's been known for some time. So it has several proofs. The first, at least the first that I know of, goes back to Lucho Avramov and Ragnar Bookweitz. This is the support variety paper. And so the idea here is the way that they show Betti complexity and Bass complexity are the same. It's basically reducing it to the hypersurface case. And then we already talked about it there, right? Betti complexity would just be the constant Betti numbers, and the Bass complexity in that case would be the constant Bass numbers. And so we already said those were the same. So that was the strategy there. There's a nice paper of Lucho again, and this time Srikanth Iyengar in 2010, I think. So here the idea is to reduce the problem to showing this is true over an exterior algebra over a field. And then the idea there is that obviously an exterior algebra over a field is self-injective, and then you can play around with that. So it's, again, kind of reducing the problem to a different setting. This also follows from work of Greg Stevenson, 2014. So here the strategy is completely different. Here the idea is to classify the thick subcategories of the singularity category over R, and from there you can deduce this complexity statement pretty easily. And kind of in a similar fashion, there's a paper by Jian Liu and myself in earlier this year. It was published, and again, it's kind of a similar idea as showing that thick subcategories are closed under duality. So using over a complete intersection ring. So using that fact, you can also prove this statement. So there's kind of several different ways you can argue it for the complexity statement. And then I guess Ben, Daniel, and I have a slightly different proof, but it's closer to the original Avermaet-Bookvitz proof. So, so I just want to point out though is that the Betti degree and Bass degree, that's really the meat. That's the main point of all of this. That's the hard part of the proof. And part of what makes it difficult, so, is that Betti degree and Bass degree are more subtle. They're more subtle invariants. So, for example, if I look at the Betti complexity of a direct sum, that doesn't actually change the complexity. Right. So this invariant, as far as the additive structure goes, just with direct sums, like you can't see direct sums. Whereas when I'm calculating the Betti degree of direct sum, you have properties like this. So I mean, and if you're interested in thick subcategories and things like this, I mean, again, the story is, the story is that two objects can have the same thick subcategory in the derived category, and yet the Betti degrees certainly don't need to be the same, whereas the complexities do. And the same story is true for the Bass complexity and Bass degree. So this invariant is just a little more subtle. It's just a little harder to get your hands on. So that's. So if anything, I mean, yeah, this is the main part of the theorem. Okay, so that's the theorem. And what I should do is give you some idea of what goes into the proof. So that's what I want to do next. So okay, so the main ingredient are what are called cohomological jump loci. Okay, and so I just want to remind us of this, of the setup. So, R, or the completion, is some regular local ring modulo some Q regular sequence. Okay. And so in this setting, I think this is pretty well known. So in this setting, there's a graded case subalgebra. Call it S. And in fact, it's a polynomial ring that lives inside of XKK. Where I'm thinking of XKK, it's like the Uneta X algebra, right? So it can equip it with the composition product, if you like. And these chi's, they live in cohomological degree 2. So and these are sometimes called the Eisenberg operators or the Gullickson operators, right? So, okay, and so what makes S, one of the things that makes S useful is the following fact, due to Gullickson, is that when I look at X MK, this is a finitely generated graded S module, where you might ask, well, how is it acting on this? Well, the point is you have, S including into XKK, and then there is a natural action of XKK on XMK, right? Just post-composition. And so S is acting just by restriction of scalars to the composition action. And so, typically these X modules are, infinite K-spaces, infinite dimensional K-spaces, yet when you include these operators, you kind of shrunk this down to just a finitely generated S module. Okay, so this has been known for a long time. And so, but yeah, these operators have been very effective at getting homological information about modules over complete intersections. And so that's kind of the same story here. Okay, so so in 2000, in the codimension 2 paper, Avramov and Bookweitz, well, they show that this action lifts to the chain level. So what I mean by that, namely, one can equip Arham MK with the structure of a perfect DGS module. Okay, so all I'm saying here is that there's some model for this, for which this thing becomes an honest, perfect DGS module, and I'm going to call this X sub m from now on. And so the point is that the S action on this induces the S action of Eisenberg and Gullikson. So it's the same S action. That's all I'm saying here. But the point is that working at this chain level gives you kind of finer information, right? Because you're not taking homology first, right? And so that's important for the perspective of these cohomological jump loci. Okay, so let's do some quick examples. So if you want to go and compute X sub K itself, so that's Arham KK, right? It turns out, and I'll be a little bit sloppy about the shifts, this is just S, and then it's the exterior algebra on S where you take the embedding dimension. So this is just the minimal number of generators, the maximal ideal. Okay, so that's one example. Another example is when you do R itself. Well, that's easy enough, right? When I plug in R, I just have K here. But over S, we know a model for this. This is the Kazul complex. KC as an S module. Okay, so I'm working at the chain level rather than taking homology. But in these two cases, okay, those are kind of easy calculations. So now I'm ready to tell you the definition of the jump loci, and then I'll try to tell you, kind of how you use them to prove the result about Betti degree and Bass degree. So the ith cohomological jump locus, of M is, right, so it's denoted VR of M, and so what it is you take the points, in the homogeneous spectrum of this ring S, this polynomial ring S, and okay. So let me write it down, and I'll try to explain the various pieces of it. All right. So, okay. So just to be clear, this is the homogeneous spectrum of the polynomial ring S, right? Where this is, again, just to remind you, this is the polynomial ring on C variables where the variables have degree 2. And this is equipped with, of course, the Zariski topology. And here, I'm talking about the graded field. So I do the homogeneous localization at this homogeneous prime, and then I go modulo that homogeneous maximal ideal. And so this homology module here, this is just some graded KP space, right? So it has some well-defined rank. And what we're asking for is that the ith locus is only including the primes for which this rank is bigger than I. So we're only including the primes for which the rank of this object jumps up to the ith spot. Okay, so I'll do some examples. So hopefully I'll clarify what's going on here. But yeah, maybe I'll just. But yeah, okay. So maybe example is probably the right way to go here. So let's consider the case for m equals k. So just to remind you, in this case, this is the exterior algebra on this. And so if I take any prime, any homogeneous prime in S, and I look at x sub k tensored over, well, I would, in theory, want to do derived tensor, but this thing's already free, so I tensor this with kp, and what we get is just an exterior algebra on the embedding dimension. And so and it turns out there's no differential, so when I try to take homology, I'm still left with this, and I want the total rank of this kp vector space, okay? So it turns out it's just 2 to the embedding dimension. Okay, so what does this tell us? This tells us at the end of the day that when I go to compute these cohomological supports, it's going to be constant. It will include every prime up to 2 times the embedding dimension. And then after this, it's going to jump down to the empty set. +1. Okay, so this is, sorry, not doing good on spacing. This is the empty set. And so from there on, all the rest of the jump loci are empty. So this sequence of jump loci, maybe it doesn't seem terribly interesting for this example. The point is it stays constant all the way up to 2 to the embedding dimension of R. Then it literally jumps down to the empty set from there on. Okay. Actually, can I ask real quick? Do I have? Is it 5 more minutes or 15?
No, it's 15 more minutes.
Oh, 15. Okay, good. So yeah, I want to do another example. But this is the kind of behavior that these jump loci always have. So what we're interested in is when the varieties change, when these sets change. So let's do another example, and then I'll mention a couple properties of these sets. Okay, so let's do x sub r. So x sub r we said was k, but we said we know what the free resolution is over S. It's this right here. Okay, so for this example, what I'm looking at is the Cazul complex on these chi's, tensor Kp. And so now there's 2 options, right? So if I look at the irrelevant ideal, right, then I'm just going to get, well, I'll write it like this, even though it's just K, right? I'll get Kp to the C, right? Because all I'm doing is modding out by the chi's themselves, right? So all these become 0, so I'm left with an exterior algebra, right, over a field. Okay, So in this case, Kp is K. But for all the other cases, if P is not the irrelevant ideal, then we've inverted one of the chi's, right? So now I'm looking at a Cazul complex where one of the elements is a unit. And so you get 0. Okay, so what does this tell us? So this tells us that the sequence of jump loci for R itself looks a little different. And for this example, we have the following. So we're always going to have the case the 0 locus is all of spec S. And the point being is that this condition is vacuous, right? The rank of a K vector space is always bigger than or equal to 0. So it always starts as large as possible. But then in this example, it jumps down at the first step, and then it's equal up to the 2c step, and then it jumps again at the 2c plus first step, and that's when it becomes empty. Okay, so along the way in the middle, so all of these ones, this is just supported at the irrelevant ideal, right? So that's corresponding to this calculation right here, right? So everywhere along the middle, it's just supported at the irrelevant ideal. Okay. So let's see. So kind of a not terribly difficult fact is that for any M, any finally generated R module, what you always have is that the sequence of jump loci for M, they always start off as large as possible, and they're just some nested sequence of closed subsets where eventually you have to get to the empty set at some point, right, where these are closed. Okay, and so I did two kind of, I guess, like easy examples where you see in this first example, right, for K, the sequence is stable and then it has one jump down to the empty set. And then there's a slightly different example where, there's two jumps, right? So it's supported everywhere at the beginning. Well, I mean, not really, but, the 0th locus is spec S, and then it's only supported at the irrelevant ideal, and then it jumps down to the empty set. So I should, right, okay. So let me just think about how to finish this. Okay, so the point is that these jump loci record the Betti degree. So that's the upshot of studying these things. So let me tell you how this works. So I want to revisit the theorem. All right, and so, of course, we said the Betti complexity, which this first one's already known, right? The Betti complexity and Bass complexity are the same, but we'll rederive it, and then the Betti degree, the Bass degree are the same. Okay, and the main point are these jump loci. The sequence of them records the Betti degree. So, okay. So I just want to give you the big picture, the steps involved. So step 1 is to reduce to the case of full complexity. So maximal complexity you could ever have is the codimension of the complete intersection. So you reduce to this case. And then what you can show is, so in this case, you can read off the Betti degree from the sequence of jump loci. So what you do is you look at the max I such that VRI is equal to the homogeneous spectrum. Okay, so in terms of kind of this chain of closed subsets, what you do is you look at the very last spot, so VI, before it jumps down. You look at that very last spot, that number I. So whatever that number I is, if you divide that by 2, that tells you the Betti degree. Okay, so it's this last spot. Okay. So that's kind of step 1. Step 2 is that you show that these varieties are invariant under duality. These closed subsets are unchanged by duality. And here, this star, this is again the same duality we've been working with. This is just the derived dual. But if you'd rather work with an MCM module, this is the ordinary R linear dual. Right? So I'll show this. Step 3 is a kind of a classic calculation that goes back to the Licho, Avramov, and Ragnar book fights, is that the beta complexity of M star is the same thing as, by the Hilbert-Serre theorem, it's the same thing as the dimension of the first variety for M star. So this has been known for some time. And then this dimension right here is the same as the dimension of the variety of M because of step 2, right? Doesn't depend on the dual. But again, the same logic tells you that this is the Betti complexity of M, which we said was maximal. So it had maximal complexity. Okay. And so in this case, we also can say what the Betti degree of M star is. It's 1/2 the max over all I such that VRI M star this time is spec homogeneous spectrum. Okay. But again, by step 2, by the fact in step 2, and I guess this equation up here, right? So the fact that the Betti degree can be read off as that max degree for which the varieties are equal to the full spec. Combining that with this, what we can say is that the Betti degree of M star is the same as the Betti degree of M. All right, and finally, step 4 is just use that we have a Gorenstein ring. So use the Gorenstein duality again. So R's Gorenstein implies that if I'm looking at the Bass complexity of M, that's the same thing as the Betti complexity of M star. And the Bass degree of M is the same as the Betti degree of M star. But up above, we've already showed that this is the same as Betti complexity and the Betti degree of M. Okay, and so I think those are the steps involved. I got a little bit more time, but I'll stop here. I'll just maybe mention, so some of the arguments here are using that we have a Gorenstein. Using that we have a Gorenstein ring, but some of the results hold more generally for modules of finite CI dimension. There you kind of just don't have step 4 working. So you can show that for modules of finite CI dimension, the Betti degree of M and its dual are the same, and so hence those leading terms are going to agree for the quasi-polynomials for Betti numbers of modules of finite CI dimension. So, okay, but I think it's a good place to stop for today. Yeah.
Thank you, Josh, for your interesting talk. Let us all thank him.
Thanks.
So we are open for any questions. You can unmute and ask your questions.
Okay, I will ask a question.
Sure, sure. Yes, Mohan.
So in the X algebra, X I K K,
Mhm.
you had that subring, right?
Mhm, mhm, mhm.
But that for a complete intersection ring.
Yes, right.
What happens if you just have a Gorenstein ring? Is there a natural subring of that object? I mean, some natural structure that you can think of? Just Gorenstein.
Yeah, I don't.
No, it's okay.
Not that I know of. No, I mean.
Okay. Thanks.
Yeah.
Thanks.
So working, if you are curious though, if you're working, if you just have a module of finite CI dimension, there is a way to kind of identify a certain subalgebra, but also kind of the right place to be working is with Hochschild cohomology instead. That's kind of the the right place where these operators will always. So yeah, exactly. That's a good question. I mean the operators in this case can naturally be identified with some subalgebra of XKK.
I know.
But I would more generally kind of work with Hochschild maybe, and then you can always have the operators working there. So.
Okay. Thanks.
Mm-hmm.
Right. Are there any other question? Josh, I have two very naive questions.
Right.
So when you write this Betti polynomial and the Bass polynomial asymptotic value,
Yes.
so these are integer valued polynomials. So
no, or they're rational, or integer value. Sorry. Yes. Yep. Sorry.
Yeah. So when we deal with Hilbert polynomials, we write them in terms of binomials, and then the coefficients have many interpretations. And so what happens in this case, if you write it in terms of binomials, do some things emerge?
I don't. I mean, I think this term is coming from that usual binomial
Right.
expression. This term is kind of the mysterious one, right? And I think where this comes from is, if you remember, those operators have degree 2.
Mm-hmm.
And so that scaling, I think, has to change the normalizing factor, right? It doesn't have to, but
Yeah.
But yeah, I don't know I don't know what the other coefficients would be
Right. And the coefficients of lower powers of I, do they have homological interpretation?
That's a great question. Yeah, I mean, we don't know. I mean, one thing that's true. I mean, one thing that's clear from these examples, right, is that you can't. I mean, they're not going to be the same, right? Yet the jump loci are always agreeing. So, I don't know. I mean, I guess that's something for us to think more about, how to relate the jump loci to lower coefficients. But I don't think we really have a good idea of how to do that yet.
Yeah.
I have one question. So do we have some information regarding that from which, so these Bass numbers and Betti numbers, they're eventually quasi-polynomial, right? So do we know from which stage onwards it is true? Is it some project dimension, or do you have some information that from which stage onwards it is going to be quasi-polynomial?
Yeah, I didn't. Oh, that's a good. I mean, yeah, it's a good question. I don't. Yeah, sorry, I don't know the answer to that question.
So in this example where you have this monomial forming a complete intersection, at what stage does it become quasi-polynomial?
in these two examples, they become quasi-polynomial immediately, which is interesting. Yeah, so I did these calculations and it happens right away. But
Okay.
no, so if someone can correct me if I'm wrong, but I think there's something called like the critical degree. And so this is like in a paper of Avramov, Gasharov, and Pava. And I feel like the critical degree is what you're asking about. I'm not 100% sure. I think it's something to do with like when something starts to stabilize. But I could be wrong about that. But I don't know in general when to expect it. Yeah. I'm sure other people do know though.
Yeah.
Thank you very much.
Yep.
Yeah. So, and any other questions?
So one more maybe general question. So is there any a geometric reason for these leading coefficients to be equal?
Yeah, I mean, I think that is essentially like what these jump loci are doing. They're giving a geometric reason for y, and the point is that this last jump number is telling you kind of the multiplicity. It's telling you like the multiplicity of the x module over the polynomial ring, essentially. So it's like I don't know, this spot where it jumps is somehow a geometric interpretation for why you would expect the for it to be that leading coefficient, right? Because that leading coefficient is just, in some sense, it's just the multiplicity of that module over the polynomial ring, right? So does that kind of make sense? Or?
Okay.
Okay.
Yeah.
Thank you very much.
So I don't see any further questions. So thank you, Josh. And
Thank you.
Thank Josh once again for the very interesting talk.
Thanks so much. Appreciate it.
So we'll close for this week, and we will meet again next Friday. Thank you very much again, Josh, for coming online. And
yeah, thanks again for inviting me. This